Welcome to Tech Talks, the official student run technology podcast of the Wharton School, where we host forward looking discussions that enlighten and inspire. I'm your host, Mahima Singh, and today I'm joined by Siddharth Singh from Stony Brook University. Siddharth is an AI researcher and engineer currently pursuing his master's in computer science at Stony Brook University, where he's focused on edge AI and sensing systems. His research includes developing low latency models, including light detection and ranging, for collision detection and evaluating large language models in healthcare. He has conducted research at the Indian Institute of Technology, Delhi, and the Indian Institute of Information Technology, Delhi, where he co authored a published paper at ACM SIG CHI 2024 on the state of art indoor localization system. Siddharth brings a strong perspective on bridging research and engineering to build AI systems that work under real world constraints. So, thank you so much, Siddharth, for taking out time despite your very, very busy schedule to be with us here today.
Thanks,
It's
Mahima. It's a privilege to be here. The Modern Tech Talks platform has had a remarkable lineup of guests. I look forward to the conversation.
Thank you for being with us here. So, with that, I'm going to kick off. And our first questions are just going to be a warm up. So, with that, the first question for you today is you worked across research, LLM evaluation, edge AI, and applied systems such as fraud detection and real time models. What's the difference between how a researcher versus an engineer approaches the same problem?
That's a really useful frame to open with because the difference is fundamental, and I think it's underappreciated. A researcher's primary obligation is the truth. You're trying to understand something precisely, which means you have to be willing to conclude that your hypothesis was wrong, that the effect you were looking for does not exist, or that the question needs to be reformulated entirely. The measure of good research is the rigor and the honesty of the process. An engineer's primary obligation is to a working system. You're trying to build something that performs reliably under a defined set of real world conditions, which means you are constantly making pragmatic trade offs. A solution that is 80% as accurate but runs 10 times faster and costs a tenth as much to operate may be a far better engineering decision than the theoretically optimal one. Where I found it gets interesting and where I have tried to operate is when you hold both standards simultaneously, ask, is that what I'm building? Is what I'm building actually correct? And will it actually work? At the same time, that's harder, but it's the right disposition if you want research that eventually becomes a real product.
Awesome. That's so valuable to know. Thank you so much for sharing that. And with that, we're going to drill further on the research mindset. And my second question is when you start a research problem, how do you decide what question is worth answering versus what's just interesting but not useful?
I use a few filters. Um, I'll share the ones that have been most reliable for me. The first is, does this problem have a clear failure mode in the real world? So if I can point to a concrete solution where the absence of solution causes harm. For example, a self-driving car that cannot see around the corner, a fraud system that blocks legitimate transactions, a healthcare LLM that routes patients incorrectly, then I know the problem has stakes. Research without stakes tend to stay in journals. The second is the gap between what's theoretically possible and what currently exists. Is it large enough to matter? If the current best solution is already 95% of the way there, improving it is interesting, but probably not worth the full investment of a research program. I want problems where the gap is a factor, where a meaningful improvement would change what's actually deployable. The third, and I think the most underrated is, uh, can I define a success precisely before I start? If I can't write down in concrete terms what it would look like to have solved the problem, it's usually a sign that the problem isn't well formed. That definition process is often where the real intellectual work happens.
Thank you for sharing that. That's just really, really helpful to know and get your perspective on from somebody who's already published so highly. In your experience now, our third question, what does a good research problem definition look like? And how is it different from how business problems are usually framed?
That's an interesting question. So I would say a good research problem definition basically specifies the input, the desired output, the constraints, and the evaluation criteria to understand whether we have reached a particular solution. And doing that with enough precision that two independent people would agree on whether a given solution constitutes progress. Business problems, in my experience, tend to be framed around outcomes: increase revenue, reduce churn, that is the amount of money you're spending towards production, improve customer satisfaction. These are valuable goals, but they're not research ready. To get from a business outcome to a research problem, you have to work backwards through a chain of questions. First, what decision needs to change to affect that outcome? What information would enable that decision? What is the gap between the information we currently have and the information we need? And lastly, is usually where the last question is usually where the research problem lives.
Sounds good. Thank you for sharing that. And my follow up question to that is, in your LLM evaluation work, how did you design evaluation frameworks? What does it take to rigorously measure something as fuzzy as AI performance?
I would say this is one of the most practically important challenges in applied AI right now. And I'll share how we approach in the healthcare context specifically. The project involved evaluating ChatGPT, Gemini, and Llama on postnatal care queries, essentially asking, can you trust these models to support clinical decisions making for new mothers? The first thing we recognized is that AI performance in this context is not a single number. It's a multi-dimensional construct, and you have to decompose it. We defined rubrics across several dimensions: clinical accuracy, appropriate hedging, completeness, and what we called a failure taxonomy, categorizing the ways models were wrong, not just whether they were wrong. A model that says, I'm not sure, please consult your doctor to every question, is perfectly safe, but has zero utility. A model that answers confidently but with outdated general guidelines is dangerous. Those are completely different failure modes that require different mitigation. The broader principle is before you can measure something fuzzy, you have to make it less fuzzy. You do that by defining what good looks like, what bad looks like, what the critical failure modes are, and then building evaluation instruments that are sensitive to those distinctions. It is closer to psychometrics that is standard benchmark evaluation, and most teams don't invest nearly enough in it.
Thank you for sharing that. With that, our next set of questions are going to be about learning, engineering, and system building realities. And question 5, once you move from research to building, what changes? How do constraints like latency, compute, or real world noise reshape your approach?
Almost everything changes in practice, and I think the single most important shift is in what counts as a valid solution. In research, you optimize for a metric under controlled conditions. The model that achieves the best benchmark score wins. In production, you optimize for reliable performance under the full distribution of real world conditions, which includes inputs your model has never seen, hardware that's slower than your development environment, network conditions that are unpredictable, and maybe edge cases that your training data didn't cover. In the NLOS collision detection work, for example, we are building a system that needed to run in real time on a Raspberry Pi, a constrained embedded device under varying lighting conditions with target moving unpredictably. Every architectural decision had to be a stress test against the constraint profile. A model that achieves excellent results on a clean benchmark data set, but fails when the target moves unexpectedly, or maybe when the light levels change. It's not a valid solution for the deployment context, as it won't work in the real-time conditions. That's a fundamentally different design criteria than research publication. I would say the practical implication is that in production, you're not designing a model, you're designing a system. The model is one component, pre-processing pipelines, inference, optimization, monitoring, graceful degradation under failure. Those are equally important and they are largely invisible in research literature.
Awesome. Thank you so much for sharing that. Now, coming to our next question, you experimented with multiple models like classic ML versus neural nets. How do you decide what to actually ship versus what just performs well in experiments?
I would say the decision framework I've developed comes down to three criteria, and evaluate them in roughly this order. First, does the model's performance generalize to the development distribution, not just the test set? A model that performs well on held out data from the same distribution as training is doing something. But the more important question is, does it hold up when the distribution shifts? For fraud detection, that means transaction patterns that weren't present when the model was trained. For edge AI sensing, that means environmental conditions that differ from your data collection setup. Second, what is the cost of failure and does the model fail in a recoverable way? A neural network that fails confidently, outputting high confidence wrong predictions, is often worse than a classical model that fails noisily and predictably. In safety critical systems, predictable failure modes are often worth more than marginal accuracy gains. Third, does the inference compute requirement fit the deployment budget? This is where neural nets frequently lose to classical approaches in edge settings. A well-tuned gradient boosting model that runs in microseconds and is fully interpretable can be preferable to a neural network that runs in tens of milliseconds and operates as a black box, even if the neural network is technically more accurate.
Thank you so much for sharing that. So, building on that, our next question, can you share an example where the best model technically was not the right choice for production?
Yes, I would say the weaker in-cabin noise filtering project that I did at Indian Institute of Technology, Delhi, is a good example. We evaluated several approaches for real-time denoising, including neural network-based methods that perform better on our accuracy metrics in offline evaluation. The neural methods produced cleaner output in control tests. However, when we evaluated against production constraints, the need to run in real time on embedded automated hardware with strict latency budgets. Without a GPU, the neural approaches exceeded the available compute envelope. They also had worse failure behavior when they encountered input distributions outside their training range. They failed in ways that were hard to predict. The Kalman filter, which is a classical statistical estimation method developed back in the 1960s, met the accuracy threshold that mattered for the deployment context, ran within the latency and compute budget. and critically failed in ways you would characterize and reason about. We could understand why it would degrade under specific conditions, that transparency had significant value for engineering team responsible for maintaining the system. The lesson I take from that is best is always relative to a context. The model that is best for a research paper and the model that is best for a deployed product are often different, and conflating them is one of the most common and costly mistakes in applied AI.
Thank you so much for sharing that perspective. That's so useful and so agree with you. Best is relative to context. So, with that, our next set of questions are going to be focused on learning more about iteration, failure, and truth. Um, what does your experimentation look like from hypothesis to testing to iteration?
I'll describe the experimentation loop as I actually run it rather than the idealized version. It would start with a precise hypothesis, not, I think a neural network will work here, but something like I believe that treating the sensor histogram as a time series sequence will allow the model to capture motion patterns that are predictive of collision events, and that this will outperform a single frame classification approach by at least X on our evaluation metric, X being like suppose 50% more than what is there currently. The specificity matters because a vague hypothesis produces a vague conclusion. From there, I design the minimum experiment that can falsify the hypothesis, not the most comprehensive experiment, the minimum credible one. This is a discipline I had to develop deliberately because the instinct is always to build a more comprehensive setup, but a simple, well controlled environment that clearly answers one question is more valuable than a complex environment that produces ambiguous results. When results come back, adversar- I try to be generally adversarial with my own interpretation. Before I conclude that something worked, I ask, what's the most plausible alternative explanation for this result? Is it possible that I'm seeing a data artifact rather than a real effect? What would I have to observe to be confident this generalizes and works in every situation? Iteration is driven by the gap between what the hypothesis predicted and what the experiment showed. If the results match the hypothesis, I typically tighten the conditions, test it in a harder environment, reduce the training data, stress test the failure cases. If results don't match, I try to understand why before I change the model. The reasons a model fails are often more informative than the failure itself.
Thank you so much for sharing that perspective. Um, Coming to our question 9 for today. In your experience, what are the most common ways AI systems fail in the real world that MBAs don't anticipate?
Uh, I'll give you the four I see most frequently because they're very distinct failure modes. The first is distribution shift. For example, there, whenever there's a major event that happens, it leads to a data shift. For example, models trained before the COVID-19 pandemic might not work after the pandemic, like 1 to 2 years after the pandemic. When the real world changes, economic conditions, user behavior, environmental conditions, the model's input no longer looks like what it was trained on, and the performance degrades silently. The insidious part is that the system often continues to produce outputs that look plausible, even as it is actually showing just reliability drops. This is why monitoring is not optional. You need systems that can detect when the model is operating outside its reliable range. The second is metric misalignment. The metric that was optimized during development is often not the metric that matters for the business outcome. We optimize for accuracy and fraud detection. The business cared about the ratio of fraud losses prevented to false positive rates. Those are related, but not identical. And optimizing for the wrong one can produce a technically high performing model that might be operationally very harmful. The third is the cold start problem in deployment. Models trained on historical data that often perform poorly on new users, new products, or new geographies where little data exists. This is rarely fully solved in research, and it hits immediately when a system goes live. The fourth, the fourth one, and this one surprises people, is human behavior adaptation. When you deploy an AI system that makes decisions or service recommendations, people respond to it. Fraudsters adapt their behavior to evade detection models. Clinicians adjust their practice based on AI recommendations in ways that create feedback loops. The system changes the environment it's deployed in. Very few teams model for this at a design time, and it produces failures that are genuinely hard to anticipate from a static evaluation perspective.
Thank you for sharing that perspective. With that, our next group of questions are focused on bringing together the perspectives from, the personas of program manager, research, and engineering interfaces. So, our question 10 for today. From your perspective, what's the difference between a PM who works well with research and engineers versus one who slows things down?
The
And
distinction,
a PM here is a program manager or a product manager.
uh, I would say the distinction I've observed is fundamentally about whether the PA treats uncertainty as a problem to be eliminated or as information to be managed. A PM who slows things down typically wants certainty earlier than the process can provide it. They push for committed timelines before the scope is understood. They escalate ambiguous results as failures rather than as part of the normal research process. And they translate research questions into business requirements without doing the work of understanding what the research can and cannot commit to. This creates pressure that leads to either premature commitment or defensive sandbag, which are both expensive. A PM who accelerates the work understands that research and engineering have different time horizons and different relationships with uncertainty. They help the team be precise about what is known, what is unknown, and what the plan is for reducing uncertainty rather than trying to eliminate uncertainty by fiat. They protect the team from organizational pressure to move faster than the problem allows, and they translate between research progress and business milestones in a way that maintains both credibility and momentum. The practical skill underlying this is the ability to distinguish between we don't know yet, which is normal and manageable, and we have a real problem, which requires escalation. PMs who can make that distinction reliably are generally rare and very valuable.
Thank you for sharing that perspective. And my next question there is, how can MBA students better translate business problems into something engineers and researchers can actually act on?
The most important shift is learning to ask what decision needs to change before asking what model should be built. The framing I find most useful is a business problem is typically a situation where someone is making a consequential decision with insufficient information. Your job as the person translating that problem is to identify precisely which decision, what information is missing, and what form that information needs to be in to actually change the decision. That decomposition process usually reveals that the problem is narrower and more specific than it initially appeared, which is exactly what researchers and engineers need. Concretely, instead of we need to churn a prediction model, the more actionable framing is our retention team has a budget to contract at risk customers 30 days before renewal. They can contact up to 500 per week. And we need to identify which customers are most likely to churn in the next 30 days if not contacted. That framing immediately tells the engineer the output format, the time horizon, the scale, the operational constraint, and implicitly how the model's performance will be measured in production. The second skill is learning to write crisp problem statements that include what success looks like and what failure looks like. Engineers and researchers make better decisions when they both know what the boundaries are.
Thank you for sharing that perspective. And with that, we've come near to the last question now. So, closing out our last question for you, and thank you for all the valuable perspectives you've shared today. If an MBA wants to become a strong AI product manager, what should they actually learn to understand both research and engineering teams?
I'll build on to that answer by giving you three things that I think are genuinely high leverage rather than a long list.
Sounds
First,
good.
develop enough technical literacy to detect that something is being hand waved. You don't need to be able to build models, but you do need to be able to ask precise questions about how a system works, understand the answers well enough to know whether they are credible. The goal is not to become an engineer, it's to not be misled very easily. That requires understanding the basic vocabulary of model evaluation, deployment constraints, and data quality, which you can develop through a handful of good courses and hands-on projects. Second, build genuine intuition for the research to deployment gap. Spend time with engineers who have shipped production ML systems and ask them to walk you through what broke. The gap between a model that performs well in evaluation and a model that works reliably in production is where most AI product failures happen. And understanding it from first principles will make you a significantly more effective PM. Third, and this is the one I would prioritize, get very good at formulating precise, answerable questions from ambiguous business situations. This is the core translation skill, and it's the one that creates the most value at the interface between business strategy and technical execution. It is also a skill that MBA programs are well positioned to develop if you deliberately practice it on technical problems rather than only on strategy basis.
Sounds good. Thank you so much, Siddharth. This has been super valuable to learn your perspective and firsthand get perspectives from a researcher. And we've come with that to the wrap of our interview today. Thank you for taking out the time to be with us here despite your super busy schedule. It's been a true pleasure and an honor to host you. So thank you so much again for being here.
Thank you, Mahima. This has been a genuinely stimulating conversation. I think the questions were pitched at exactly the right level for an audience that bridges business and technology. I hope it's useful for the modern community.
Thank you so much, Siddharth. Thanks a lot. And to our viewers, if you enjoyed this episode, be sure to subscribe, rate, and leave a review on Spotify or Apple Podcasts. You can also follow us on the official Wharton Tech Club LinkedIn and at the rate Wharton Tech on Instagram to stay updated on upcoming guests and new episodes. Until next time, thank you so much and see you around. Thank you again, Siddharth.